In the last video, we talked about SQL and NoSQL databases, but we left a critical question unanswered. How do databases themselves scale? A single database node, no matter how powerful, has limits. It can only store as much data as fits on its disks. It can only handle as many queries as its CPU and memory allow. And if it crashes, everything is down. Two techniques solve these problems: replication and sharding. Together, they're how Cassandra handles trillions of rows, how PostgreSQL serves millions of queries per second, and how databases stay alive when hardware fails. The most common replication pattern is primary replica, also called leader-follower or master-slave. One node is the primary. It accepts all writes. All changes are then replicated to one or more replica nodes. Replicas can serve read queries, distributing read load across multiple machines. This is a common pattern for read-heavy workloads. A news site, for instance, might have 99% reads and 1% writes. One primary handles all writes. 10 replicas handle the flood of reads. There's an important trade-off here: replication lag. When a write happens on the primary, there's a small delay before that change appears on the replicas. During this window, a read from a replica might return stale data. This is called eventual consistency. The replicas will eventually catch up, but there's a brief period where they're behind. For most applications, this is acceptable. For financial transactions, it's not. Some databases support synchronous replication. The primary doesn't acknowledge a write until at least one replica has also written it. This eliminates stale reads at the cost of higher write latency. Let's quantify the replication lag. In a well-tuned PostgreSQL setup on the same local network, asynchronous replication lag is typically 1 to 100 milliseconds, imperceptible to users. Across regions, replication lag is bounded by the speed of light, roughly 70 ms from US East to US West, 150 ms from US to Europe. Cross-region replication means cross-region lag, and your application architecture must account for it. The choice between synchronous and asynchronous replication is a consistency availability trade-off in miniature. Synchronous replication: zero data loss, higher write latency, primary can stall if a replica is unreachable. Asynchronous replication: possible data loss on primary failure, the window of in-flight writes that haven't been acknowledged by replicas, lower write latency, primary never stalls waiting for replicas. Most production systems use asynchronous replication for performance, with synchronous replication to at least one replica as a safety net. Multi-leader replication, also called active-active replication, is used when you need writes to be accepted from multiple geographic regions without routing every write through a single primary. Consider a global application with users in the US and Europe. With single-leader replication, all writes go to US East. A European user's write travels across the Atlantic before being acknowledged. With multi-leader replication, writes are accepted locally and then replicated between leaders asynchronously. The problem is write conflicts. If a user in the US and a user in Europe both update the same record at the same time, you have a conflict. Each leader accepted its local write. Now they need to reconcile. Common resolution strategies: last write wins. Whoever has the later timestamp wins. Simple, but can lose data. Merge, application-specific logic to combine the two versions. Or expose the conflict to the user for manual resolution. CouchDB, Cassandra, and Google Spanner all have different approaches to conflict resolution. Google Spanner sidesteps the problem entirely with true-time. Atomic clocks in every data center that lets Spanner assign globally unique, causally consistent timestamps to every transaction. Replication solves red scaling and availability. But what if your data grows so large that it doesn't fit on a single machine? Or your write volume is so high that even the most powerful single machine can't keep up? That's where sharding comes in. The key decision in sharding is choosing your shard key, the attribute used to determine which shard a piece of data lives on. If you're sharding a user database, you might shard by user ID. User IDs 1,000 go to shard 1. User IDs 1,000 DAOs and 2,000 DAOs go to shard 2, and so on. Hash-based sharding solves the hotspot problem. If you hash user IDs, even if your newest users are far more active, they're distributed evenly across all shards. But hash-based sharding makes range queries expensive. If you want all users created between January and March, you'd have to query every shard and aggregate the results. Consistent hashing is a special form of hash-based sharding that makes it much easier to add or remove shards without rebalancing all the data. We'll cover consistent hashing in detail in Video 8. Directory-based sharding is the most flexible approach. You maintain a separate service, the shard directory, that maps each entity to its shard. Need to move a hot user to a less loaded shard? Update the directory entry. No data movement beyond that one record. The cost. Every database operation now requires a directory lookup first. If your directory service is slow or unavailable, your entire database layer grinds to a halt. This is why directory-based sharding is most common at companies with dedicated infrastructure teams who can operate the directory with extreme care. Sharding is not a first resort. It's a last resort, or at least a late resort. The operational complexity it introduces is significant. Here is the framework for reasoning about sharding in an interview. The signal to shard. Your dataset exceeds what fits on a single node, typically above 1 terabyte, or your write throughput exceeds what a single primary can handle, typically above 10,000 writes per second. At those thresholds, you've exhausted vertical scaling and read replicas as solutions, and sharding becomes the right conversation. Choosing the shard key is the most consequential decision. A good shard key distributes data evenly, matches your primary access pattern, and avoids cross-shard queries for common operations. A bad shard key creates hotspots, forces cross-shard queries, and makes rebalancing painful. For a user-centric application, social network, e-commerce, SaaS, shard by user.id. Every query is get data for user X, and hashing user.id distributes evenly with no hotspots from sequential IDs. For a multi-tenant application, B2B SaaS, shard by tenant RID. All data for a given company lives on one shard, enabling efficient per-tenant queries. The risk is a whale tenant, a single large customer whose data overwhelms one shard. You handle this by detecting whale tenants and giving them dedicated shards. For time series data, logs, events, telemetry, shard by time range, combined with a secondary dimension. Sharding purely by timestamp creates a write hotspot. All current writes go to the most recent shard. Facebook's messages, database shards by conversation ID, so writes are distributed across all shards regardless of time. Sharding solves the scaling problem but introduces significant complexity. These challenges are important to discuss in interviews. Cross-shard queries become expensive. A join across two tables that live on different shards requires fetching data from multiple machines and merging it at the application layer. Many databases simply don't support cross-shard joins natively. Rebalancing is painful. If shard 1 becomes a hotspot because most of your active users happen to land there, you need to rebalance. Move data from the hot shard to a new one. This is operationally complex and risky. Data skew happens when your shard key isn't truly uniform. A small number of extremely active users can make their shard into a hotspot even with hash-based sharding. The classic hotspot example: a celebrity on a social network. If you shard by user arch ID and hash user arch IDs, a celebrity with 50 million followers generates 50 million fan-out write operations every time they post. Those writes all reference the celebrity's shard through the fan-out service. One shard melts. The rest, idle. Solutions: push-based fan-out with rate limiting. Pull-based feed: never write to followers, only write to the celebrity's own shard, read from followers at display time, or maintain a separate high-traffic key list and route those keys to dedicated high-capacity shards. Twitter moved from push to pull fan-out specifically because of celebrity hotspot problems. Instagram eventually landed on a hybrid: push for non-celebrities, pull for accounts above a follower threshold. A single database node, well-tuned, high-end hardware, handles between 10,000 and 50,000 reads per second with primary key lookups and drops to 5,000 to 20,000 writes per second under sustained load. Adding read replicas multiplies read throughput linearly. One primary plus 10 replicas can serve 100,000 to 500,000 reads per second. Writes remain bottlenecked at the primary. When you add sharding, write throughput scales linearly with the number of shards. 4 shards multiply your write capacity by roughly 4. 8 shards by 8. This is horizontal write scaling. Facebook operates approximately 9,000 MySQL shards for its social graph data. Not 9,000 servers, 9,000 logical shards, many co-located on physical hardware. This is the scale at which sharding operates when you have billions of users generating billions of writes per day. Cassandra achieves horizontal write scaling without explicit application-level sharding. The partitioning is built into the database itself. A 10-node Cassandra cluster handles millions of writes per second. A 100-node cluster handles tens of millions. The shard key concept exists in Cassandra as the partition key, the first part of the primary key that determines which node owns a given row. In production systems, replication and sharding are used together. Each shard has its own replica set, a primary and multiple replicas. This gives you both horizontal write scaling, sharding, and horizontal read scaling and fault tolerance, replication. MongoDB's architecture makes this concrete. A MongoDB sharded cluster has 3 components: Mongos, the query router; config servers, the shard directory; and individual shards. Each shard is itself a replica set. You query Mongos. It consults the config servers to determine which shard owns your data. It routes your query to that shard's primary, or a replica for reads. The application sees a single database. The complexity is hidden behind the router. This architecture pattern, router, directory, shards with replicas, is not unique to MongoDB. It's the general pattern for any sharded, replicated system. Vitess, MySQL sharding at YouTube, Cassandra's coordinator nodes, Redis clusters hash slot routing, all follow the same shape. 3 mistakes that consistently cost candidates points on sharding questions. Mistake 1. Recommending sharding too early. Interviewers test for this. If your system has 10,000 users, you do not need sharding. If your system has 100 million users, you might. If your write volume is under 10,000 per second, a well-tuned single primary handles it. Recommend sharding only when you can articulate why simpler solutions are insufficient. Mistake 2. Choosing the wrong shard key. Candidates sometimes propose sharding by a timestamp. Shard by created at. This creates a sequential write hotspot. All current writes pour into the most recent shard. A good interviewer will catch this immediately. Always validate your shard key against the question: does it distribute writes evenly? Does it match your primary query pattern? Mistake 3. Ignoring the operational complexity. Sharding means cross-shard queries need application-level aggregation. Schema migrations become sharding-aware. Monitoring must track each shard independently. These are real costs. Acknowledge them and show you understand why companies defer sharding as long as possible through vertical scaling and read replicas. Replication solves availability and read scaling. Primary accepts writes, replicas serve reads. All stay in sync. The trade-off is replication lag and eventual consistency. Sharding solves write scaling and storage limits. Data is split across shards by a shard key. The trade-off is cross-shard query complexity and operational overhead. In production, combine both. Sharded database with replicas on each shard. Shard when your dataset exceeds 1 terabyte or your write volume exceeds 10,000 per second. Choose a shard key that distributes writes evenly and matches your primary access pattern. Facebook runs roughly 9,000 MySQL shards. A single node handles 10,000 to 50,000 reads per second. Sharding multiplies this linearly. In the next video, we tackle one of the most important and often misunderstood concepts in distributed systems, the CAP theorem, and what it tells us about the fundamental trade-offs in every system we build. See you in video 7.